This video is about understanding right ascension and time. Right ascension is measured in some sort of hour, which you might have already learned. You should have already learned hours, minutes, and seconds, but it's not hours and minutes and seconds of time, or is it? It could be confusing, but I want to help you understand that coordinate, right ascension. So this video assumes you already have plotted uh, values on a grid, right ascension and declination. But what is right ascension all about? Why hours, minutes, and seconds? So we're still working on this set of objectives, and the first few objectives, one of those things is being comfortable with right ascension. There's also a concept called sidereal time. We're going to talk about that in this video. So that's what's going on in this video. Um, Latitude on Earth, if you're on Earth looking at the sky, your latitude determines how far north or south you see on the celestial sphere. But what determines how far east or west? Well, east or west on a sky map is measured in hours. Right ascension is measured in hours, minutes, and seconds. An hour is actually 15 degrees. And then a minute of right ascension is 1/60th of 1 hour, and so on. But what does that mean? Well, it's measured in hours. Why does it go backwards? Right ascension goes to the left. All of this makes sense, but you need to see it. It's not obvious at first. So hopefully you're already comfortable plotting the coordinates or using the coordinates. You can find the coordinates on a map, but how did it ever get labeled like that? That's got to puzzle you. Well, hopefully we're going to answer that. If it's puzzling you, we're going to try and answer that question. Here is an activity you can do with Stellarium Web, and it's easier to see this than to explain this. So I want you to pause the video if you need to, try to set this up in Stellarium, and do what it shows here. So I have some screenshots where I'm using Stellarium Web. I want you to go to the View Settings, which is in the upper left-hand corner, the menu icon, and then View Settings, and then choose Meridian Line. So we already talked about what a meridian line is. It's a line that kind of divides your sky into two halves, the east half and the west half. The meridian line goes from north to south. If you have it set up like that, you're going to see a green line in Stellarium Web, your view. There'll be a green line labeled meridian. Now, click and drag the sky and rearrange it so that you put south at the bottom. That's one thing I don't like about Stellarium Web, is the default setting is it has you facing north. However, I think that you will find it easier to orient yourself if you put south at the bottom. So imagine you're facing south. You need to click and drag to set it up like that. And then turn on constellations and equatorial grid, which is these things down here at the bottom. So that's the constellation icon. Here's the equatorial grid, not the azimuthal grid, but the equatorial grid. So that's the one that shows right ascension and declination. Notice at the top, you're going to have to look closely, but there are some numbers you got to look. They're almost hidden, but they're labeled H. So 16H, 17H, 18H, where I'm pointing with the laser pointer there, 15H. Those are lines of right ascension labeled 15 hours right ascension, 16 hours right ascension, and so on. So that's the setup. Get it set up. And then try this. So what you're going to do is open up the time control box, which is down here where I'm pointing the laser. You're going to click on that, and that brings up this box where you can click forward a year or a month or a day or an hour or a minute or a second. You can move back and forth in time. This resets the time to the current date, and you can pause. And then you have a slider, and you can rapidly go, change the time by dragging the slider. But here's what I want you to try. Drag the slider forward, go forward in time, and look at those right ascension lines. And how much time does it take to go up by 1? you want to use the meridian line as your pointer. So if we're looking at the right ascension on the meridian line, and then you go forward in time, how much time does it take to go up by 1 hour of right ascension? Do the same thing with the day clicker. So instead of using the slider, click on the date. So my screenshot here shows 9:14. What if I click and go to 9:15? Does that move me forward 1 hour of right ascension or not? If it's not, then how many days do I have to click to get forward 1 hour? So please pause the video and try this. You can go back and forth in the video if you need to see the instructions again. So try it and see what you find. Okay, so I want to show you, hopefully what you found is what I can show you with a similar program. This is Stellarium, the app that you can download. And if time is going forward, and with it's a little bit different, but I can just say make time go forward. We can see the celestial sphere going by. And I have this set up where we can easily see the right ascension. It might look a little small to print, but there's 0 hours, 2 hours, 4 hours. So that's my meridian, just like in Stellarium Web. And here comes 4 hours on my meridian, and then 5 hours on my meridian, and then 6 hours on my meridian. So hopefully you can see why the numbers go that way. Oh, they make sense that the part of the celestial sphere that I'm viewing when I look at the sky is always going up in right ascension. So now I'm looking at the 10-hour line of right ascension. Now I'm coming up on the 11-hour line of right ascension. That's the sun, that big bright thing, but the program is showing me the grid, even though we wouldn't see any stars during the daytime. Um, so how much do I have to move forward? Well, let's look at time. So I'm going to open up this little time window here, and let's pause time. So I'm going to pause the time, and then let's just go forward. So I'm just going to back up a little bit and say, oh, look, I'm right on the 18-hour line. What if I go forward 1 hour? Oh, wow, now I'm on the 19-hour line. I hope you figured that out for yourself. But if you didn't, that's the connection. Wow, that makes a lot of sense now. If I go forward 1 hour in time, I'm now looking at the next hour of right ascension. So I go forward another hour, and now I'm looking at the 21-hour line. I hope you see what I'm pointing at. If I go forward another hour in time, now I'm looking at the 22-hour right ascension line, and so on. If you look closely, here's something that's a little puzzling and a little bit annoying. If I keep going forward by 1 hour increments, it's not exact. Darn. So I've gone forward an exact number of hours, but I'm not exactly on an hour line anymore. But it's really close. So what happens is there's a very close connection between going forward an hour in time and going forward an hour in right ascension. It's not exactly the same, but it's really close. If we zoom in on it, we would be able to tell a little bit better. So I might do that, zoom in. I went too far. So here's the 20-hour line, and now we've zoomed in. Let's go back and let's see precisely how much time. So there, my clock down here says 22:49. If I go forward 1 hour, I may be a little bit too far to get to the next line. Am I right on top of it? It's kind of hard to get it exactly where you want it, but we could adjust the seconds, maybe get it right on top of that line. If I go forward an hour, forward another hour, I can already see I'm off by a little bit. And that gap keeps changing. Every time I go forward an hour, I keep getting off a little bit further. So, but it's a very close connection, and that's one of the things that you need to get. What about the days? So you had a question about days. Let's try that one too. How many days? If I don't change the time of day and I go forward a number of days, how many days to get from 1 hour to the next? So right now I'm on the 5-hour line. So here's 4 hours, there's 6 hours. Let's go forward. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 or 16 days, about 2 weeks would move you forward 2 hours if you're looking at the same time of day. All I want you to get out of this is that there is a connection between right ascension measured in hours and time going forward. Now we have hopefully established that right hours of ascension kind of makes sense. It's really close to what our clock on the wall does. However, it leads to a concept called sidereal time. So we're now going to take some notes and look at some definitions of what we call sidereal time. Sidereal time is an important idea. The sidereal day is an important idea. And we're going to be talking about various time concepts that relate to astronomy. Astronomy is a kind of where time, some of the ideas for time come from astronomy. So I feel like that's an important thing to learn about astronomy is the connection, all the connections with time and the way we judge time. So let's get going here. So what is sidereal time? We just saw it. If you were paying attention and you got the Stellarium web to work and you saw how I was using Stellarium, this should make sense to you. Sidereal time that we saw in Stellarium is defined by the right ascension of the meridian. And that's what we were calling out when we were looking at the animation. Oh, here goes the 0 hour line. Here goes the 1 hour line. And as we were watching, we could see, oh, there goes a certain line, a certain right ascension. When it crosses the meridian, that's what time it is. If we judge time by the stars, the word sidereal means of the stars. So translates from some old language and basically means of the stars. So it's the time based on stars. And right ascension on the stars is kind of like a clock made out of stars. So if you want to know what time it is, if you could see those lines, you could just look up in the sky and say, oh, it's 3 hours right ascension because that line is right on my meridian. It's called sidereal time. Sidereal time depends on your location and the date and time. It's sometimes called local sidereal time if we're talking about what it looks like to a particular person. So if I go out, I see that the 3 hour line, for example, is on my meridian, then my sidereal time is 3 hours. This is a little bit like we have different time zones on Earth, so that if I'm in Knoxville, the time is different than the time is in California. 3 hours difference. Well, you know what? There would be 3 hours difference in sidereal time also. So that's another similarity. Again, this is something that has a name, has a concept. Sidereal time and local sidereal time is just what you would observe if you actually went out and looked. It depends on the locale, so that's where local comes from. Based on sidereal time, there's something we call the sidereal day. So a sidereal day is the time for the stars to do their thing. So every night the stars rise and the stars set and the stars go across the sky, a little bit like the sun does. Of course, the sun is also a star. But the stars do something a little bit different. So the stars rise and set like the sun, and it takes a little bit less than 24 hours for the stars to do that. So here's an odd thing about what we call the sidereal day. It's close to 24 hours, but not exactly. It's about 4 minutes short. Now you can look up the value. It's actually 23 hours, 56 minutes, 4 seconds, 4.09 seconds. But for simplicity's sake, we often just say, oh, it's about 23 hours, 56 minutes. So it's 4 minutes shorter than a regular day. A regular day is 24 hours. So what is this sidereal day? Sidereal day is a day based on stars. That's why it's called sidereal. Sidereal is of the stars. 23 hours, 56 minutes is the time for a star to rise and then set and then come back to where it started. It's the time for that cycle of the stars rising and setting. Because a sidereal day is not 24 hours, sidereal time is not the same thing as the time on our clock, the clock on the wall. And it also is why we noticed, 1 hour of right ascension was not exactly 1 hour of time on the clock. So that's an important distinction. What is a regular day? What are our clocks based on? Well, the clock on the wall is based on the sun. That's called the solar day. If we're going to give a special name to a day of stars, we need a name for what we call a day normally. What is a regular day? Well, a regular day, what we're really used to is, hey, the sun came up, went down, came back. That's a day. We know that. And we know that a regular day, a solar day, astronomers would call it, is 24 hours. And exactly 24 hours, right at 24 hours, not 4 minutes difference, just right precisely 24 hours. And that's what our clocks are based on. Clocks on the wall tick off 24 hours, and then the sun is back where it was whenever you started that. So this is the time for the sun to do its thing, the sun to rise and set and return to its original position. That's the time. Our clocks are based on the sun. If we had clocks based on the stars, it would be a little bit different, 4 minutes difference in what a day would be. Now, you might have noticed the word mean. Mean solar day is kind of a technicality. It turns out that the time for the sun to do its thing changes a little bit from day to day. So it can vary a little bit throughout the year, but on average, it's 24 hours, and it's always very close to 24 hours. That's kind of a technical thing. We can talk more about that some other time. I have an animation that should help you understand the solar day and the sidereal day. Let's suppose you go out and you're looking at the star, or not the star, looking at the sun, and here's you. You're standing out in a yard somewhere, and you're looking south, kind of, and here's your horizon. And it's 12 p.m. 12 p.m. is noon. So it's noon, and you're looking at the sun. And then let's fly forward in time. There goes the sun. Nighttime. Here comes the sun again. Well, a day went by, so it's noon again. We often think of noon, high noon, as when the sun is high in the sky. So the red line in my animation represents a meridian. So imagine the sun goes around, sets in the west, comes back, rises in the east, and goes back to the meridian. That should take 24 hours. It does. That's a day. But now, what if we did the same thing with a star? We depend on the sun. We pay attention to the sun. So the sun is the most important thing kind of governing our lives. It's our day-to-day lives. Well, what if we were, I don't know, maybe we could just say, well, I'm obsessed with this star. I'm going to live my life by this star. Every time the star comes up, I'm going to go to work. And every time the star sets, I'm going to go home. And then I'll do the same thing. Maybe I'm a weirdo and I refuse to go by the sun. I want to go by a star. Well, let's watch what happens with a star. There it goes. It's going to set in the west. Day goes by, daytime goes by, and here comes my star. My star is going to get back to the meridian a little bit before midnight. So I started that at midnight, and then by the time the star gets back, that's 4 minutes before midnight. And that is a sidereal day. That is the time for a star to go around and come back. You probably didn't know that, but the stars take a little bit different amount of time, 4 minutes difference. The stars do it in 4 minutes less time. But look, there it goes again. The star gets back to here. That's another 4 minutes lost. So every regular day that goes by, the star is going to be crossing the meridian 4 minutes earlier because it takes less time for the star to go around and come back. Let's try kind of a little exercise. Let's suppose that it's 12 p.m. noon, that's solar time. That's what time our clock says on the wall if the sun is high. But it might be something like 18 solar or sidereal time. I'm sorry, ST stands for sidereal time. If that were true, then the meridian is on the 18-hour line. And then a day goes by. So here we go. Let's do our animation again. Sun sets, stars go by, sun comes back. What are those two times going to say? Well, the clock on the wall is going to say 12, but the sidereal time is going to be different by how many minutes? 4. 4 minutes. Let's see what the values are. Oh, wait a minute. Why did sidereal time go forward 4 minutes? Because the sidereal day is faster. So this is kind of a different way to look at it. The sidereal time would actually be a little bit ahead of where it was the previous day because a sidereal day goes by faster. 4 minutes less time for it to happen means it's happening faster. If we want to, we could try a different one. Let's start at midnight. So 12 a.m. is midnight. Suppose it's 5:58 sidereal time. This star has a right ascension 5:58 because it's on the meridian. And now we can run forward and say, okay, what happens by the time the star comes back? Now what am I going to say? Well, the star came back to the meridian, meaning the sidereal time is the same, but the solar time is going to be different. So the sidereal time is still 5:58 because the same star is on the meridian, but now my solar time is off by 4 minutes. So there's just this 4 minute discrepancy between these two kinds of time. Are we judging time by the sun or are we judging time by stars? All right, so what we have here is an animation I created to help you think about clock time versus sidereal time. Remember, the clock is based on the sun, and that's the one we're very familiar with, 24 hours in a day. What if you could see those right ascension lines your whole life? Anytime you wanted to, you could just look up in the sky. So what I have here is an animation where we're trying to imagine that. And before I animate it, let me point out a couple of things. So here you are, you're out in the yard, here's south on the horizon, and you happen to have a clock. Clock time is going to be indicated by this little arrow, the little white arrow. And then here's your meridian, the red line. And sidereal time is just whatever is in that little box. So as the celestial sphere rotates, we're going to see the number there change. So I can look at what number is lined up with the white arrow or what number is in this little red box. That's how I've got it set up. And I'm just going to click run and let's watch what happens. So I have it set up right now that midnight is clock time and I have it lined up with 0 hours. Now let's run forward. And what you're going to notice is that for a while it seems to be synchronized. So we're coming up on, say, 9, and when the clock said 9, the sidereal time said 9. And now we're coming up on, well, 15 is 3 past noon, and then 18 is 6 past noon, and so on. And by the time we get back to midnight, we're pretty much back to 0. So that was 24 hours of clock time, and it looked like 24 hours of sidereal time. But I set up this animation carefully. The two wheels are not spinning at the same rate. So if we keep watching, we're going to start to notice a slight discrepancy between the two times. So now we're coming up on midnight again. Are they coinciding? Ooh, did you see that? I think the 0 hours went by before midnight went by. Let's look for 9. So here comes 9. 9 hours sidereal was a little bit before 9 on the clock. So I hope you're seeing what I'm seeing. I'm just looking at both of those times. Here we're coming up on midnight again. So 0 hours, is it going by? Oh, it went by before the clock got to 12. And that's the way it goes. The sidereal time, the wheel goes around once in 23 hours, 56 minutes. The clock time is completed in 24 hours of time, what we normally call time. So this is just a different way to show it that the hours that we put on the celestial sphere are not quite the same as the hours on the clock, but they're close if we could view it as a giant clock in the sky. Okay, let's get a little practice with sidereal time and right ascension, the connection between time and right ascension. So I have a set of three questions here that you can answer using a star chart. You don't need anything else. Just get some star charts out, and we'll do these problems. You can pause the video and try it yourself. So number one, let's look at number one. Suppose the constellation Orion is centered high in the sky early one evening. How many hours later would Leo be centered high in the sky? So if you were out looking at the stars and you say, oh, there's Orion right on my meridian. And then how many hours later would Leo be right on your meridian, right in the middle of your view? So we're going to answer that question. You could pause the video if you want to try it first yourself. Get a star chart, find Orion, and see if you can figure it out. Find Orion, find Leo, and think about what you have learned about right ascension. Pause if you want to. So here I'm going to answer the question. So I'm going to activate my laser pointer. Here's Orion. And the question was, if Orion's right in the middle of my view, how many hours later or how much later in the night would Leo be right in the middle of my view? Well, we saw that the hours of right ascension, which are shown at the bottom, are pretty close matched to the hours on the clock. Not exact, but pretty close. So I'm just going to look at this and say, look, Orion is kind of centered between 5 and 6. I'm going to call that 5.5. And then if I look at Leo, Leo is kind of centered on 10.5. So from 5.5 to 10.5 is 1, 2, 3, 4, 5. I can kind of see it in my mind's eye, what we saw in the animations, that, okay, if time goes by, this guy is going to rotate, and 5 hours later, I'm going to be looking at Leo. So that's going to be my answer, 5 hours. 5 hours later. So here are my questions again, and I've added the answer that we just came up with 5 hours later. But now let's look at number two. So if the star Deneb has a transit, the word transit in astronomy means something going through the meridian, crossing the meridian, switching from the east half of the sky to the west half of the sky. That's called a transit. I've crossed the meridian, so transit means to cross. So if Deneb has a transit at midnight, what time does the star Vega have a transit the same night? When would the stars transit the next night? How about a week later? So let's try and figure that one out. And again, you might want to try and answer the question yourself, pause the video, get a star chart, find Deneb, find Vega, and then see what you think the answer is. So I'm going to answer that question, and let's activate our pointer again. So sometimes it's hard to find these things on a star chart, so good luck, but I'll help you out here. So here's Deneb, here's Vega, and we're asking the question, what time? So we want to look at that and notice, oh, we have these two stars, Deneb and Vega, and I think it said Deneb was on the meridian at midnight, but to get to Vega, I'm going the other way, so that's 1, 2. That must be not later in night, but earlier in the night. So it must have been 2 hours earlier. Vega would have been on the meridian and having a transit. When a star crosses the meridian, it's said to be transiting. But again, I can use basically the hours at the bottom, the lines of right ascension, to judge like how many hours. So it looks like 2 hours earlier. So here we are back at our questions and some answers now. And I showed you how to get 10 p.m. So Vega is 2 hours to the right of Deneb on a star chart. And that means it's going to be getting to the meridian before Deneb, because to go forward in time on the star chart, we need to go to the left. So if Deneb is transiting at midnight, Vega should have transited 2 hours before that, so 10 p.m. What about these other questions? We can figure those out without having to go back to the chart. Remember, a sidereal day is 4 hours shorter than a regular day. So Deneb would get back to the meridian, crossing the meridian, having a transit 4 minutes before midnight, 23 hours, 56 minutes after the previous midnight. And Vega would do the same thing. So now my times would be shifted by 4 minutes. They would be 4 minutes earlier. Remember, the stars are faster, so they're going to get there faster. How about a week later? Well, a week, 7 days, every one day is 4 minutes. So 7 days would be 7 times 4, 28 minutes. So these would become what, 11, and then subtract 28, 11:32 and 9:32 is what it would be a week later. So every day that goes by, another 4 minutes difference. Now let's look at this last question. An observer is located on the prime meridian. That's a place on Earth. And they see the star Fomalhaut on the meridian. So she's looking at the meridian and she sees Fomalhaut. Some people say Fomalo, so that one I'm not sure how to pronounce. At the exact same instant in time, an observer at what longitude sees Antares on the meridian? That's another one sometimes people say differently. Antares, some people say Antares. Doesn't really matter. So let's look at our chart, see if we can figure out the answer to this one. Okay, so here's the chart we need. Fomalhaut is right here. It's a part of a constellation Pisces Austrinus, the southern fish. So Fomalhaut is right here on the 23-hour line. Antares is over here in Scorpius. Antares is right here on about 16 and a half on our grid. So what's the difference? 23 to 16 and a half would be a difference of what? 6.5 hours of right ascension. But this time we're talking about the same point in time. Well, 6.5 hours of right ascension is a certain amount around the sphere. Here's a good time to remember, oh, this is like a giant sphere. 24 hours equals 360 degrees. So every one of those hours is a jump of 15 degrees. So I've got a jump of 6.5 hours of right ascension. 6.5 times 15 is going to tell me how far away from the prime meridian. And I'm moving to the right on the star chart, and that is west on a star chart. Here's our final slide summarizing these 3 questions. And these are questions just designed to help you think about and force you to think about right ascension, how it connects to time, also a little bit how it connects to longitude and time, that last question. So again, what we saw in the last question was Antares is a certain number of degrees around on the celestial sphere, and we can judge that by counting the hours. 6.5 hours of right ascension times 15 is 97.5 degrees. And it was west of Fomalhaut on the chart. That means if you were west of the prime meridian by that amount, you would have a view of Fomalhaut. At the same time, somebody on the prime meridian would have a view of, I didn't say that right. If you were 97.5 degrees west of the prime meridian, you would have a view of Antares. At the same time, somebody on the prime meridian would have a view of Fomalhaut.